Good morning and or afternoon, everybody. Hope you are all doing well. Today I want to go over electron configuration. I want to go over the worksheet I had you doing the other day. And I also want to go over more in depth some of the videos I had you watch last time. So let's start off just kind of on our white screen with a recap of, actually let me do open in page, a recap of the work we've been doing. So we've been talking about electron configuration. Electron configuration is basically a naming and numbering system to keep track of where the electrons are in an atom. It has a few main parts. First, it has what's called a principal quantum number. This is like the energy level, kind of. This is 1 through, in our case, right, the highest you can really get is 7. Right, this is the principal quantum number. After that, we have, right, each principal quantum number is followed by a followed by an orbital subshell. These are the S, P, D, or F. For us, we really just focus on S and P. And lastly, we have our number of electrons. So, number of electrons in each orbital. So when we look at our first principal quantum number, we go in order. You can't get to number 2 without going through number 1. So our first one for any element is 1 with the first shell, S. Now the first row only has access to the s orbital. So we just have one s. After that, in the second row, we can get 2s and 2p. Then we can get 3s, we can get 3p, and we can get 3d as well, although that gets a little more complicated, so I'll come back to that later. This, for the most part, is going to encompass 90% of all of the electron configurations you'll do, if not more. You need to know the numbers of electrons that's going to be in them, though, and it's going to go into these shells in this order. 1s, followed by 2s, followed by 2p, followed by 3s, followed by 3p. The s shells signify areas. You can think of them as like rooms or houses or whatever for the electrons that can hold 2 each. The p orbitals can hold 6 in total. Alright, so 6 here. So if we look at all this, we can see 2, 4, plus 6 is 10, plus 2 is 12, plus 6 is 18. Where is 18? 18 is argon, a noble gas. So when you completely fill all the orbitals on a layer, you get a noble gas. But let's look at how to do each one. Let's start off by choosing an element. Let's do silicon. Silicon is element 14. That means we have 14 electrons. So let's start off by putting 2 in here, 1s2. That's where the first 2 go. We're down to 12. The next 2 go in 2s. Now we're down to 10. The next 6 electrons will go in 2p, 2p6. Right now we are down to 4. The s orbital once again can hold 2. We'll put another 2 in there. We're down to 2 left. And then finally we get 3p2. So our full formula for silicon would be 1s2, 2s2, 2p6, 3s2, 3p2. This is the electron configuration method of writing this element. Now you can actually count these out by knowing where the s orbitals are on the periodic table. Right here, this is called the s block, in addition to hydrogen and then helium. If an element is in one of these, then its last electron is going to be in an s orbital. Then we have our p block. Well, really it extends down here as well. P and s. If it ends in here, then it's going to be the s orbital, and it literally goes in order, right? P1, P2, P3, P4, P5, P6. There's 6 of them. S1, S2. Right, and then you just apply whatever level you're looking at. If you want the D block, right, this is the D area, and this is the F area down here. But again, we're mostly focusing on the S and the P right now. So, let's do another example. Let's do an example of magnesium. It's in the S block, so it should end in S, but let's check that. Magnesium has 12 electrons. With 12 electrons, first we have 1s, that's getting 2, 10 left. But then after 1s, our next lowest is 2s, which also gets 2. We're down to 8. But now we have access to the p's. So we go 2p, we'll put in all 6. We're left with 2. And now the next lowest thing, right, you don't have anything else on the 2's other than s and p, so we have to go back to 3. 3s, and we'll use both of ours to get 2. This is for magnesium. So we have 1s2, 2s2, 2p6, 3s2. Again, looking at this, we can look and we can see the magnesium is in the S area. It's the second one in the S area, and it's on the third. So it should end in 3s2. However, it has all of the parts that came before that. So even just going backwards, you can say, well, that's 3s2. Before that, it had, right, 12, 11, that's both covered by the S's. These, it had the 2p6, right? It had the 2 p's. Then it had the 2 s's. Then it had the 1 s's. So you never skip over things, right? You always just are adding, you're always expanding on a previous electron configuration of a smaller element. But writing these can take a while. In fact, I can actually show you if we wanted to do oganesson, it's the 7th row, right? Oganesson would be 1s2, 2s2, 2p6, 3s2, 3p6. Now you'll see a slightly different order from what you might expect. I'll explain this at a later point, so don't worry about it. But 4s2. Now we go 3d10, 4p6, 5s2, 4. Nope, I have to do. Check. Nope, not yet. 4d10, 5p6, 6s2, 4f14. Right, we have 5d10, 6p6, going all the way over here, 7s2, 5f14, 6d10, 7p6. That would be the electron configuration of oganesson. You don't need to know how to do that, don't worry. Instead, I'm going to teach you a shortcut so you don't have to worry about ever writing something like this if I ask you to write something big. We can use something called a noble gas configuration. We can look at what the previous noble gas was and use that as a substitute. So, for example, previous noble gas from oganesson was radon. The noble gas configuration of radon would actually be, all of this whole thing right here, leading up to 6p6. So, if we want to just do a shortcut, all we need to do is write radon in little brackets, which is short for all of this. It's basically a substitution, like in math. Radon, 7s2, 5f14, 6d10, 7p6. That would be a much, much shorter way of going about writing that. In addition, you could argue that you could also just write that, since it is one of the noble gases. But this is generally how you do it. You take the noble gas before, you add everything that came after it. Let me check our time. 13 minutes. Okay. So with that, I'd like to go over our worksheets and kind of talk about what those meant. So for this one, I used something called POJUL, which is a popular chemistry worksheet thing. So this first part, I wanted you to look at pictures of this boarding house. A boarding house is a place where people go to stay and live, right? They are boarded, which means to give them housing. And it describes two different types of rooms, sunny rooms and pink rooms. The sunny rooms are just a clever way of saying s orbitals. That's why it's in S. The pink rooms are p orbitals. That's why it's a p. And the manager's code is just a way of saying, right, it's just the electron configuration. So, let's look at each of these. The time is just ignore that. First, we have one person in the first floor sunny room. It can hold 2 people all together. And remember, this is a boarding house, so it's not like a hotel, right? The sunny room has a bunk bed that can hold 2 people. But the manager in charge of finding a place for everybody to sleep, and he likes to put them in order and leave these rooms, leave the top rooms empty until they're full. He says, okay, I have one person in the first floor sunny room. So first floor sunny, one person. Here we look, and on this first floor there are 2 people in that bunk bed. So he says, okay, first floor sunny room, 2 people. Then he goes on to look at the upstairs ones. The second floor sunny also gets 2 people. So second floor sunny, 2 people. And then lastly, we get the pink rooms, or the p orbitals, right? These ones can hold 6 electrons, and for the rooms, they can hold 6 people. There's one person in each of the 2 bunk beds. Now, although the rooms like to be filled in order, right? Bunk beds fill one at a time, right? I mean, why would somebody want to sleep on a top bunk when there is a bottom bunk if, they're past the age of like 6? So, orbitals work the same way, right? We'll get into something later in the later on with arrows, where essentially they get up arrows or down arrows, but pretty much when you're looking at them, you always add a 1 box at a time. So 1 bed at a time in this case. So we look at this next one, right? It's added a 3rd person in this bed, and then it goes back and it's a 4th person in the first one. So now instead of 2p2, it's 2p4. Getting to this one, right, we have 2 people in the first floor, 1s2, 2 people in the second, 2s2, 6 people in the second floor pink. So second floor pink, 6, 2p6. And finally, we have 1 person in the sunny room on the 3rd floor, so 3s1. Right, continuing, same deal here, except we have 2 people there, so 3s2, but now we have a 3p1. And here there's 1 in each bed, so we have a 3p3. For a noble gas configuration, again, you can cut off anywhere where there's a noble gas. All noble gases, because they're all the way in this row, end in p6. So you would be able to look at this and see, okay, here's a p6. You could make a configuration for that. As an atom, 3s1, right, that is going to be third floor, sorry, the third floor, third row, S area, 1, sodium. To write the abbreviated configuration, though, you could write, we have to look at the previous one. The previous one is neon. So you just say, in parentheses, neon 3s1. All right. So for this one, right, the labels were just, sunny room, bunk, border, things like that. So for the above one asked how many boarders are in the house, you literally just count the dots. 1, 2, 3, 4, 5, 6. There are 6 people looking for rooms, just in the same way that a 2s2, 2p2 atom, which would be, we look for our second row, we look for the second one of the p1s, carbon. Carbon has 6 electrons, just like this has 6 borders. Matching the symbol, right, we can look, so the floor number in that case, right, 2p4, the floor number is 2 because that comes first. Saying the second floor, the p room, it has 4 people. Number of borders in the room. Or for our chemistry purposes, right, number of electrons in the orbital. These boxes are ways that we write these configurations. We get 1s, 2s, 2p, 3s, 3p. We add them, one arrow represents 1 electron, and we can add them one at a time, first up, then down, pretty much in the same exact way. All right, I think I have it selected to give you automatic feedback on this. So if you feel like you need more than that, please let me know. Beyond that, I am going to go over, sorry, I am very, very tired. I've been in the hospital all day. I am going to go over the worksheet I posted. So for these, right, and make sure you turn in your work, people. I saw not everybody turned them in. All I have is going off of credit. I am not in there. I can't look at your stuff. I can't look at a piece of paper. So turn it in, or it's going to end up being a 0. This first. Here we go. So let's talk about electron configuration for copper. If we look over here at copper, we can see, actually, you know what? I apologize. I had meant to upload this with a list of things to ignore, including, sorry, copper, bismuth, and zirconium for this one. You know what? I apologize. I'm going to post the answer key for this, and I'm going to focus on going over the ones I need to do more in depth for that. I'm sorry. I think I was just blanking out yesterday. Like I said, going to the doctor so much, I think I had just completely lost track of that. If you're having trouble with this worksheet, don't worry about it because I did not do enough preparation for a lot of these. My apologies. So, we have configurations, which the following electron configurations belong to which elements? 1s2, 2s2, 2p6, 3s1. In this case, whenever you need to identify a configuration of an element, what you should do is just look at the very last, sorry, if you need to identify an element from a configuration, look at the very last one, 3s1. We want to go to our periodic table, look for the third row, the S area, 1 electron, which is actually, we already have pulled up, sodium. Third row, S area, first one, 1 electron. just clear this out. There we go. So let's keep going with that though. Now we want 4d6. So the D area is here. But this is actually where it also gets tricky. This is 3D. This is 4D. We go 1, 2, 3, 4, 5, 6. Ruthenium. Alright, now we have an abbreviated one, which is going to be 4d10 after krypton. This is just going to be the last of the D areas. Cadmium. Now we have 6p2. We want to look for the one that ends at 6p2. And get rid of this. There we go. Row 6, p2. Lead. We also have 6d4. So if we look at this, right, we have 6, right? But this is 5d because it's always one row behind. So now we do, okay, 6d4. 1, 2, 3, 4. Borium. Now let's look at these and try to determine if these electron configurations are correct or not. In order for an electron configuration to be correct, right, it has to have the correct number of electrons, which we don't know what the correct number is, so, you know, we can look at that by counting, and they have to have been added in the lowest order, so you completely fill all of the smaller orbitals before moving on. In addition, they do have to go in a correct order. So let's look here. This first one doesn't have the 3D. This is supposed to say 3D instead of 4D, so this one's wrong. This next one, 1s, 2s, 2p, 3s. This is a correct configuration. The 18 here, we have a noble gas configuration. So first, let's check on radon. Radon is right here. Anything coming after it should have 7s. After 7s, we should have our 5f's and our 6d's. However, our f's aren't full. They're supposed to be 14. So this is not a correct configuration. Here, we have argon, 5s, 4d10, 5p5. Everything appears great at first, but then we notice that argon comes before row 4. So there shouldn't be any 5s here. They should be 4s, or argon should be traded for krypton. Here we go. So, and finally we have xenon, 6s2, 4f10. Xenon comes right before 6s, so 6s2, 4f10. That would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Californium. So, let me check our time real quick. Alright, we're at about 30 minutes. I'm going to be completely honest. I was going to keep going and doing more examples. I am exhausted and feel like I'm about to fall asleep. So I think I'm going to end recording here and supplement it with another YouTube video that does more practice problems of these and shows you how to do those. I am sorry, guys. Have a great day. As an apology, I'll leave you with a quick fun fact. I had a good one just earlier. I can't think of that one, so I'll go with another one. During the Crusades, there were a band of soldiers with leprosy They would fight together. They were devoted to their cause. If you touched them, you might get leprosy. They knew they were going to die anyway. And due to the damage from leprosy, they couldn't feel pain. As a result, they ended up being one of the most effective and powerful units in the entirety of the big crusades, the major one. There's several different crusades, but this is the one with King Richard the Lionheart and Saladin and all that. So, have a great day.